I imagine you're familiar with the concept of water. Maybe you've gotten caught unprepared in a rainstorm, or watched ducks hang out on a pond, or had a snowball fight, or swam in the ocean. If so, you are witnessing part of the water cycle. But the water cycle, or the hydrologic cycle, if you want to get multisyllabic about it, is more than just what we can see and splash in. The hydrologic cycle links together the atmosphere, the soil, and all the living and non-living parts of this planet. The hydrologic cycle is a continuous moving system of interconnected parts that are all driven by, perhaps surprisingly, the sun. As the sun heats surface water like lakes, rivers, wetlands, oceans, or even a puddle, the water evaporates into its gas form, water vapor. Wind currents transport that water vapor all over the place and eventually condenses into clouds. And maybe you've heard, but in certain conditions, clouds drop rain or snow or hail that brings the water back to the surface of the earth in a solid or liquid form. So far, you probably learned all of this before kindergarten. If that raindrop or snowflake lands in surface water, well, it just joins into the mix. However, if it lands on solid ground, several different things could happen. The water could infiltrate down into the soil, eventually becoming groundwater, filling in all the spaces between the soil and rock. Or instead of going down into the soil, it could move across the land in a process called runoff. Now, runoff, with the help of topography and gravity, will eventually take it to another body of water, like a lake or river. Or instead of becoming groundwater, runoff, or staying on the surface, that water droplet could be evaporated back into the air by the sun's heat. From surface water to air and back again is the primary loop of the hydrologic cycle, but there are a lot of potential detours along the way. And a pretty important one, if the water enters the ground, it's now accessible to plants. Water is an essential ingredient for photosynthesis, and plants suck it up through their roots so they can steal the oxygen off of that H2O and release it into the atmosphere as breathable oxygen. Thank you, plants. Any excess water not used in photosynthesis is also released through the process of evapotranspiration, in which water evaporates out of small holes in a plant's leaves and then enters the atmosphere once again as water vapor. A single molecule of water can take quite the trip, flowing downstream, running across the land, diving deep underground, solidifying into a glacier, melting, evaporating, and condensing within the atmosphere, even hanging out in the bodies of animals and plants. Water, in whatever place and form that we find it, is one of our most valuable natural resources. I mean, we use water for everything, for drinking, for bathing, for literally staying alive, cleaning, irrigating crops, and making consumer products. Countless industrial activities like mining to spinning the turbines at power plants require lots of water. In the United States, the average person directly uses between 80 and 100 gallons every day. And that doesn't even count all the ways that we indirectly use water to do other stuff. We need to understand the hydrologic cycle so that we can best protect our water resources, because water is so important to human and environmental health. We know that many rivers get their water from rainfall and runoff, but where that runoff travels on its way to the river can affect the water's quality. If the river is fed by runoff that traveled through, say, an agricultural area, it could pick up pesticides or herbicides or fertilizers that are used to grow crops. And that may impact living things who call that river home or use the water there for their own purposes. And if that river is a source of drinking water, well, it may no longer then be safe for us. Understanding the twisted paths that water takes from the sky to our water sources is the first step in protecting those resources. And there's a million of those paths depending on where you look. And we call one of these water paths in any particular area a watershed. A watershed is an area of land that drains into a single larger body of water. All land on Earth is part of some watershed, and sometimes multiple watersheds. And a few can be really big. The Mississippi watershed, for example, contains thousands of square miles of land that eventually drain into the Mississippi River. But even on a smaller scale, all of this shaded area is part of the St. Johns River watershed. If you zoom in, here's a small tributary that flows into the St. Johns River. This land is simultaneously part of the small tributaries watershed as well as the larger watershed of the St. Johns River. Watersheds on watersheds. Between larger watersheds, there's often a drainage divide. That means something in the topography or the land surface makes a water droplet on one side flow one way and the other side another way. A common divide? Mountain ranges. High elevation points often separate two different flows of runoff across two different watersheds. Topography isn't the only thing that affects how water moves across a landscape. Organisms, for example, can dramatically alter an ecosystem and the flow of water. Take a beaver, for example. Their dams can transform a flowing water ecosystem, like a river, into a wetland, with slower moving water and more trapped sediment. Before European colonists arrived and turned all the beavers into hats, North America was home to perhaps 400 million beavers. That's between 5 and 30 beavers on every kilometer of stream or river on the whole continent. And much of the fertile soil in the American West got there because of beaver dams. Wetlands act as natural speed bumps and filters, slowing the flow of water across the land and cleaning it as it passes through. Wetlands are also habitats to many species of plants and animals. If the beavers are removed, either from overhunting or habitat loss, then that entire watershed would be altered. The wetland habitats would shrink along with any biodiversity those wetlands had. Organisms like beavers that have profound impacts on an ecosystem are called keystone species. And their presence not only affects the food web and the other organisms that interact with it, but the very structure or survival of the local ecosystem. Keystone species are ecosystem engineers, sometimes literally in the case of the beaver. To maintain and improve the health of our watersheds, keystone species need to be protected. And there's a lot of those keystone species and watersheds that need protection. Why? Because of us. Surprise! Humans also have a massive impact on watersheds. Every house, road, farm, mine, and sewer changes how water flows through an area. If heavy rain happens in a city, well, that water probably won't seep into the ground. Most urban areas are covered by impermeable surfaces like streets and roofs and sidewalks and parking lots. So in urban areas, because the water can't go into the ground, there is lots of runoff. Urban stormwater runoff is its own category, spawning entire municipal water management departments because it's become such an issue. And as that stormwater runoff moves across these impermeable surfaces, it can pick up lots of different pollutants. Candy wrappers, cigarette butts, oil, gas, pigeon poop. When this urban runoff eventually does enter a nearby body of water, it's still carrying all that pollution with it. And if there's enough rain, all this stormwater runoff can lead to massive flooding of dirty water. Just like air pollution in the last lesson, it is important to remember. A pollutant in one place, well, it seldom stays there. The water cycle and movement across watersheds carries that pollution far and wide. In an effort to protect watersheds, the United States has passed two key pieces of legislation. The Clean Water Act of 1972 allows the Environmental Protection Agency to set limits on water pollutants and to require improvement of water quality from certain sources of pollution. Secondly, the Safe Drinking Water Act of 1974 specifically focuses on maintaining the quality of the water that we drink. It sets uniform standards for drinking water, including the maximum contaminant levels allowed. Water quality isn't the only thing that we have to worry about protecting. All the impermeable surfaces that people have created also have negative effects on water quantity. All that water falling on sidewalks and parking lots where before there were fields and forests now flows across those surfaces and doesn't seep into the ground, which means it doesn't replenish the groundwater. Now, we're missing out on two things here. One, the soil isn't able to filter out who knows what pollutants and trash that the water picked up on the surface. And we'll talk more about that in our next video about soil. And two, it also means we're often pulling water from aquifers or groundwater deposits at a faster rate than they can be replenished. This is what's happening with the Ogallala Aquifer in the United States, which is the largest groundwater deposit in the world. Located in the central US and not coincidentally under heavy agricultural areas, the Ogallala Aquifer is the primary source of water for crop irrigation in the region. The water is being sucked out of this aquifer really fast, way faster than it can be replenished by rainwater in the watershed. The farmers and scientists are working on ways to better conserve water, to use it more sustainably, so that the Ogallala and other aquifers, they don't get entirely dried up. Freshwater only makes up about 2.5% of the water on the planet, and it is clearly really important to people, providing countless ecosystem services. But 97.5% of the water on Earth is saltwater. So if we're going to talk about the hydrologic cycle, we've got to talk about oceans. Or is it just ocean, since they're all connected? Oceans are obviously very big, but despite that massive volume, humans have had a serious impact on them. For instance, in the Gulf of Mexico, at the mouth of the Mississippi River, there's a dead zone. Up to 7,000 square miles of ocean with insufficient oxygen dissolved in the water to support life, that's a dead zone. Here, it's caused by all the fertilizer runoff from the Mississippi watershed, flowing into the Mississippi River and down into the Gulf of Mexico, where it causes massive explosions of algae. Now, plants love fertilizer, but so do algae. So when the Mississippi River dumps out water full of all that nitrogen and phosphorus, the algae go wild. They're multiplying rapidly into an algae bloom, and when all those algae start to die off, the decomposers come in and do their job and break down the dead algae, which pulls a huge amount of the oxygen out of the water. Now, without oxygen, most things can't live, and a hypoxic or oxygenless dead zone is formed in which fish and other marine life, they can't exist. Now, dead zones like the one in the Gulf of Mexico can be found all over the world where polluted watersheds empty into the ocean. And it has a very real human cost that can be felt far away from those coastal areas, particularly because 10% of the world's population relies on fish for their livelihoods. Now, commercial fishing is one of the main ecosystem services that the ocean provides. But just as with the over-withdrawal of water from the Ogallala Aquifer, many fisheries are overfished. Fisheries, like aquifers, aren't owned by anyone. We call these resources where everyone has access commons. Now, a commons is not private property, and it's used by lots of different people in lots of different ways. But when a commons is home to a valuable resource and economic interests start to compete, well, that sets up a situation called the tragedy of the commons. Let's say that you like to fish in a small pond near your house. It's on common land and nobody owns it, and you and all your neighbors have access to the pond. Importantly, you and your neighbors rely on that fish to feed your families. Now, if this has been going on for a while and the fish in the pond are making baby fish and their numbers are staying constant, well, that's ideal. You and your neighbors all have food. But say one week that you decide to fish an extra fish so you can have a backup, or sell that fish to someone from a nearby town. Well, then your neighbor sees you doing that and they think, oh, well, I want to make a few extra bucks too, so I'm going to take an extra fish. If that starts to happen and the fish are fished at a rate faster than they can reproduce in the pond, well, you and your neighbors are going to run out of fish. And this isn't a sustainable fishery. For the short term, it might be in everyone's best interest to fish as many fish as possible before the pond runs out. But ultimately, that's going to lead to a pond without any fish and no food or extra income for anyone. This is the tragedy of the commons. Now, this is not inevitable, and there are sustainable fisheries and sustainable forests and well-managed grasslands. But when the tragedy of the commons occurs on a large commercial scale, it can have really long-lasting environmental and human consequences. Tragedy of the commons is a bad thing. It's in the name. So how do you prevent it? Well, that's complicated. Maybe we could privatize the pond. We could put it under private ownership. Maybe that could result in better stewardship and care of the resource. Or the private owners could just fish all the fish and move on. But private ownership would also limit who has access to the pond. You and all your neighbors wouldn't necessarily have food or an income. Another solution might be legislation, passing laws and policies about how many fish can be caught per person and at what times of year. But that also requires enforcement or a collective buy-in to protect the fishery. Another tactic is education. Just inform the users about the state of their resources and empower them to use resources sustainably. That can be an effective tool to solve the tragedy of the commons. Preventing overfishing is more important now than ever because of the development of fishing technologies that can greatly increase the amount of fish caught. Things like long lines, purse seine nets, drift nets, and trawling, all aided by using sonar to help find the fish, have massively increased fishing yields, in many cases way beyond what's sustainable. Now, the goal of any solution would not be to simply ban fishing, because that's not realistic and it's not possible, and more importantly, it would be taking away the livelihood of 10% of the world. Instead, we should use scientific research to determine something called the sustainable yield. The sustainable yield is the highest rate at which a renewable resource can be used forever without reducing its available supply. In other words, we want to manage the resource not just for its current use, but also for how it's used by generations to come. This is a complicated task as well. It involves balancing the economic value of a resource and how many people consume it, counting that resource, which in the case of fish is pretty hard, The ocean is big after all, considering how land and ocean use will change in the future and modeling how climate change will impact fish stocks. It's a hard question without simple answers, but the alternative, overfishing global fisheries until there are not any fish left in the ocean, that can't be the solution. So it's hard, but it's not impossible. Fisheries in decline from overexploitation are recovering in some places due to a combination of scientific research, education, and policymaking. Take Atlantic cod. For centuries, cod was an abundant resource in the North Atlantic. Many cities and towns that exist today were built in part on the strength of the cod fishery in New England and Canada. But throughout the last part of the 20th century, cod was harvested at rates way higher than the fishery's sustainable yield. In the early 1990s, after decades of modern fishing technologies and overfishing, the population of cod completely crashed. The resource had been so poorly managed and overexploited that the fishery was no longer economically viable. In other words, it cost more to get the fish than they could be sold for. In addition to the environmental impact of dramatically decreasing this cod population, there was also the huge economic consequences, the loss of fishing jobs. But throughout the late 90s and early 2000s, a combination of science-based fisheries management plans, a few years of complete fishing restrictions, a dash of government stimulus and buyout money, and collaboration with local fisheries councils, well, the cod fishery began to recover. Unfortunately, some research suggests that this hasn't been enough, and Atlantic cod is still overfished. The ecosystem services provided by the ocean and the rest of the hydrologic cycle, they're complex, and they're without easy one-size-fits-all solutions for protection and restoration. And this is true not just for water, but everything, all of the natural resources that we rely on. Environmental science can provide some of the answers. We can build models to project watershed flows when a new project is constructed, or we can calculate a fishery's sustainable yield. But without cultural and political buy-in, environmental science alone isn't enough to protect our water systems. We covered a lot of ground, or water today. The basic hydrologic cycle, some of the ecosystem services from fresh and ocean water, the tragedy of the commons, and the difficulties in protecting global fisheries. Next up, we're going to be getting down and dirty with the underground, soil science. See you next time.